Okay, we have our sort of third in our new series trying to say what we can about the cohomology of symmetric groups that's known as we prepare to hopefully prove some new things. So today the goal, I was going to be more ambitious, but I'm going to sort of scale back a bit. And I want to just say how this Hopf presentation, and it's really, let me just put a star here because there's more descriptors, how that presentation is going to just pretty, in a straightforward ways, lead to an additive basis called the skyline basis and multiplication rules. And from there, you can, do anything you want in terms of, well, you can try to do anything you want in terms of generators and relations, or prime ideals, or other things you might want to understand in algebra. So the point is that if you have an additive basis for a ring and multiplication rules, and this is for an individual, for cohomology of SN. And the point is that the statement, which we'll get to very shortly, the statement of the cohomology presentation of these symmetric groups as all together as a Hopf ring is fairly simple. And then you have to, it's like a magic bean in Jack and the Beanstalk. You plant that Hopf ring structure in the ground, and you've got then all these amazing rings coming out, or something like that. Okay, so what is the statement? So we're going to take the direct sum of the cohomology rings of symmetric groups. Again, this is just mod 2. We're going to look over all n. That includes 0. So S0, call that also the trivial group for these purposes. And we can think of configurations of 0 points. So it's really, I don't know if that should be the, no, that would still be the 1 point space. There's only one way you can have a configuration of 0 points. So this altogether is the free, so it's a free object, but in a pretty, pretty boutique kind of one-of-a-kind category. It's a free Hopf ring, but with divided powers and a component structure, which we call incomponent. And I'll say what all these things mean in a moment. Hopf ring with generators gamma I, and this is in h2 to the I minus 1 of es2 to the I. Okay. And by the way, let me say, I'm gonna, as I said, scale back. Gamma I is represented by the geometric cocycle where 2 to the I points share their first coordinate. So the sort of first additional lecture I gave in this little series, we talked about Fox-Neuwirth manifolds with corners. These are pretty simple in the Fox-Neuwirth notation. You have one of the simpler kinds of cell names you can imagine ends up being a mod 2 cocycle, and these very simple mod 2 cocycles generate everything as a Hopf ring. So again, I think I'll do less on this this video and come back to those ideas in a bit. The relationship isn't as direct as we'd like, and there's still some a good number of open questions around that relationship. But the goal today, again, is to take this presentation and tell you about the resulting additive bases and multiplication rules that you get from this. So let's review what some of these terms are. So what Hopf means you've got two products and a coproduct. What I'm going to do is let's define this to be Rn, just the nth component of this ring. So Hi is going to be Rni if we want. So that saves us some writing. So this is the times product. In this ring object setting sense, this is the plus product. And ring objects are in the category of coalgebras. This is the coproduct. And the way these work actually is, I mean, of course, products and coproducts go from between tensor products of a vector space, the vector space that underlies a ring, to itself, or vice versa. But these impact the gradings substantially. They're governed by gradings in the sense that here, if I take something in the nth component and something in the mth component, I'm going to go to the n plus mth component. And the coproduct works sort of similarly. I'll not even sort of say, if I have R in the n plus nth component, well, R in plus m, then I'm gonna k. I'm gonna go to the direct sum of I plus j equals k, R n I tensor R m j, and it's also going to go to I have to take n plus m, or I should really say a plus b equals n plus n. So the coproduct has a lot of different sort of components to it, and we'll often just pick one, namely if delta A B is the component where I've got A and B as the labels. So this is really direct sum of the components of the coproduct map. And the times product, and that ends up being, this one is the cup product. And as you would sort of expect, if we were thinking of this direct sum isn't quite the cohomology of the disjoint union, because you would need some sort of completion. It's just the linear dual of an infinite vector space is often much bigger than the vector space itself, of course. So this isn't quite the cohomology of the disjoint union, but that's the way I like to still think about it, in which case the cup product between components is going to be 0. So really all you have is on the nth component itself. And notice that this one is doing something very different on the component labels. This goes from the cohomology of the nth component to itself. The second one goes from the cohomology of the nth tensor to the cohomology of the nth. So again, this is, let me just say that if we are thinking in terms of geometric cohomology, here we're sort of, in the first case, we're thinking of having some condition on configurations of endpoints and another condition on configurations of endpoints, and taking the intersection of those if that's transverse, and that would represent the cup product. Whereas the second thing, which is called the transfer product, means that you're taking some condition on endpoints and a condition on endpoints, and you're producing a condition on n plus endpoints, sort of by decomposing the n plus endpoints in all possible ways and seeing if those two conditions hold. Again, this will be more in the second, in a follow-up to this lecture. Right now, I'm just getting all of the algebra in front of us. So that's the Hopf ring structure. The n component is part of this. So you would, if you Rni tensor Rmj is just going to go to 0 under this product. So that's what we mean by a component Hopf ring. And divided powers means, well, you've got a divided power structure. So divided powers means you've got these divided powers operations. We use subscripts. So, and the point is that this is compatible when you've got a divided powers structure in a bialgebra. The main thing about the divided powers then is and this is a divided powers for the transfer product, for this dot, the circle product or O dot product. What that means is that the coproduct of anything, let me just go ahead and just say, we're generally going to think about our generators. The coproduct of gamma ij is going to be the sum of, or gamma I, so n is going to be the sum over j plus k equals n, gamma I divided power j tensor gamma I divided power k. So these divided powers, the coproducts, map to each other. And what that implies, if you sort of plug things in as well, right. I mean, what the divided powers for the product really means by definition, this is an implication. By definition, we have that gamma I divided powers j transfer product gamma I divided powers k is equal to the binomial coefficient j plus k, choose either one, gamma I divided power j plus k. So that's what it means to be a divided powers algebra. And then you get this coproduct formula in the sort of the bialgebra setting. Okay, so this, let me make it a little smaller. These are the rules. And again, this is this relatively short set of rules. And then the claim is that we get, from this, we get full control over both additive and then ultimately cut product structure of the cohomology of symmetric groups. And how does that work? Well, you take it one at a time. So first of all, we're generally going to let n be even, because if n is odd, it's got the same mod 2 cohomology as the previous even one. So the first interesting case, so how does this work out? Oh, let me do one other thing. So and we'll come back to this picture. We'll fill it in, and I think we'll use colors. So this says if you take the direct sum, so we take the cohomology of BS0, and then the cohomology of BS2. Again, I'm going to ignore the odds. Okay. Then what we're going to do is use colors to indicate. And actually, let me erase all this, because let me make this much bigger. And I'll go over here for a moment. And we'll come back and fill in this picture as we go along. We'll have to come back to this place in the board. So cohomology of BS0, cohomology of BS2, cohomology of BS4, cohomology of BS6. Of course, I could just say R2, R4, R6, cohomology of BS8. And let's just put in some classes that we need. I guess there's one other thing that I need to say for generators, which is over here. When I list the generators, I also need, and what I'll call 1 sub n in H0 BSN. Okay. All right. So let me just color code and add some things here and there in order of sort of complexity and where they occur in the story. So our Hopf ring generators include things like the unit class. Okay. And then what we have is in the statement, the next thing will be these generators. So I'll have gamma 1, which is in degree 2 minus 1, and then gamma 2, which is in degree 3. And then the next thing that occurs, there's not one on BS6. The next thing that occurs is on BS8. And there's a gamma 3 in degree 7. So these are sort of going up exponentially. The next one would be for BS16, there's a gamma 4. So there are those classes. Well, of course, let me stay here. BS2 is, of course, RP infinity. We often would call gamma 1x, but we're going to stick with the Hopf ring notation. So we know that at the next level, I'll choose another color, you can take gamma 1 squared, gamma 1 cubed, etc. Yeah, I guess let me try to at least start being consistent by degree. So then gamma 2 lives here. Okay, and so forth. So that's cup product on RP infinity. That's the polynomial ring, and that is implied by the theorem statement. But I also just like to think of it as a starting point to understand what's going on. And so, yeah. Then the other thing I like, I'll go ahead and do now, is to start using a graphical notation. So gamma 1, I like to make as a 1-by-1 block. These unit classes for cup product in degree 0, I like to actually think of them as an empty block, if you will. And then cup product is stacking, so things keep on going like that. Okay, it's a funny way to think about just a simple polynomial ring, but I'm going to think of x to the n as n 1-by-1 blocks stacked on top of each other. Okay, so similarly then, well, now let's start thinking about the transfer products. So in the cohomology of BS4, we have things like gamma 1 transfer product 1, 2. And you also have gamma 1 squared transfer 1, 2. And so forth. You also have gamma 1 to the I transfer gamma 1 to the j. And what is that going to look like? So now let's give some of so you have like gamma 1 transfer 1, gamma 1 squared transfer 1, gamma 1 cubed transfer 1, and so forth. You also have, for example, in this degree, you would have gamma 1 squared transfer gamma 1, and that's going to look like this. So it's also got 3 blocks. They're stacked in a different way. So this is gamma 1 squared transfer gamma 1. Right. And then you also have this new gamma 2 thing. It's in degree 3. And because so far everybody has the area equal to their degree, we can think of gamma 2 represented graphically as a block with area 3. It's got width 2, therefore it's got height 3/2. And so here are 3 things that are in the H3 of BS4. There's one other thing that we have, and you see the pattern, gamma, I'll just sort of put it up here kind of nebulously. You've got some number of gamma 1s stacked and some other number of gamma 1s. So this is gamma 1 to the I transfer gamma 1 to the j. You notice you're taking cup products to get these gamma 1 to the I monomials, and then you're taking transfer products to get from 2 monomials in BS2 to a new monomial in Hopf ring monomial in BS4. So cup product monomials in BS2, we're using those to make Hopf ring monomials in BS4. Right. There's one thing that we are missing, and that comes from this divided power structure. You have something called gamma 1 divided powers 2, and that lives in degree 2. And again, we'll just draw it up here. And you know, notice so far I haven't pictured any sort of repeated columns. So this is gamma 1 divided power 2. And that's because actually, let's looking at a relationships. So note that gamma 1 divided power 1 transfer itself is equal to twice gamma 1 divided by power 2. And of course, that's 0. So technically speaking, the transfer product from BS2 to tensor BS2 to the cohomology BS4, that's not giving us this class in degree 2, but sort of the divided power structure rather than the transfer product. The divided power structure on that transfer product is giving us this class. So that gives you these classes that would have equal numbers of columns. So let me go ahead and put it up here. You also have what we can think, what would be gamma 1 divided power 2 to the I. And that's sort of thinking about the first these pairs of columns, but if you want to make them repeated, it's got sort of a different label to it rather than a transfer product. It's this divided powers. And by the way, the conjecture is that this divided power structure is governing all of the higher torsion in the cohomology of symmetric groups. So in particular, the first class that's some 4 torsion is, let me put that as a conjecture. Well, I think I know how to prove it, but still. So here's a claim, a side claim, getting ahead on things that we are trying to do next, that the first 4 torsion is basically a lift gamma 1 divided power 2 squared, that is 4 torsion. And then and more generally, the first 2 to the k torsion is gamma 1 divided power 2 to the k minus 1, and squared for kind of standard reasons that you need sort of even dimensions for things to lift to integer classes. So these are some claims that I'd like to prove in due course, but right now let's get back to the questions of additive bases and multiplication rules. So we also, for an additive basis, you can, of course, multiply these things. Notice that, and then we have, for example, gamma 2 squared. Then I would draw that like this. So that's in degree 6. Gamma 2 cubed is in degree 9. And gamma 2 times any non-trivial transfer product by Hopf ring distributivity is going to be a non-trivial transfer product. So in thinking of additive basis, I only need to think about products of things that themselves are not transfer products. In other words, they're transfer indecomposables. And let me circle those in yellow. These are transfer product indecomposables. Okay, so so then you can add in things like in degree 5 you would have a gamma 2, gamma 3. Oh yeah, not gamma 2, gamma 1, 2. And we would represent that by this 2 block, which is the gamma 1, 2, sitting over the 3 block, which is gamma 2, not gamma 3. It's in degree 3, but it's called gamma 2. Sorry about that. Okay, and so you can keep on going there and have this is sort of where the freeness comes in. Any number of these gamma 2 blocks, which is a 3 block, and gamma 1 divided by 2 sort of decorated two-dimensional block, but it's also width 2, those can be, so this would be gamma 2 to the I, gamma 1 divided power 2 to the j. You have all of those. And I claim that that's an additive basis because, again, you might say, well, what about other cup products? Any other cup products are going to, from the statement, going to be transfer decomposable. So cup products with transfer decomposables become transfer decomposable. So claims now include that and this is the freeness, that the ring generated by this gamma 1, 2 and this gamma 2 is a polynomial ring. So it's a polynomial subring, and it's also a quotient, by the way. So it's so that's, I think, of the quote unquote new backbone, and we have these other classes which are transfer decomposable. And now let's do some multiplications. First, let's think about gamma 1 transfer 1 times itself. And what you can do is you can take its sum over coproduct. And what is its coproduct? And again, I'm only going to sort of think about the 2-2 component of the coproduct. And that's just gamma 1 tensor 1 plus 1 tensor gamma 1. And so I'm going to then get this gamma 1 now times that gamma 1. But then I also get this gamma 1 times the 1, 2, or sorry, this, I should say it the other way, this 1, 2 times the gamma 1, which would be a gamma 1. Let me write them in the same order. And so we get gamma 1 squared transfer 1, 2, because it's the unit, plus gamma 1 transfer gamma 1. But this is by divided power is equal to twice gamma 1 divided power 2, and that's 0 because we're working mod 2. And let's see how this works in diagrams. So what we're saying is that this times this equals this plus sort of this with a solid line, if you will, because of the transfer product, but that's 0, that's twice something. Okay, so that's a multiplication of two things in degree 1. Again, anything that's the general rule is going to be the transfer indecomposables have no relations, that's freeness, and the transfer decomposables, we can read off their products inductively, so to speak, from the Hopf ring distributivity. Let's try another one. Gamma 1 transfer 1, 2 times this second divided power. And what I'm going to do is start using graphical notation, because now you'll see the power of that. So it's this times this. And then what you have to notice is that the coproduct of this by the consequences of divided powers is that tensor that, and coproduct in general is going to be sort of for these perforations, these dotted lines, we're going to break along them for the coproduct. And so we're going to get something like, oh, I did this the wrong way if I want to use that coproduct. So really I should, of course the product is commutative, but let's do this the other way to be consistent with how we list Hopf-ring distributivity. Anyways, so then we've got this this coproduct transfer this other times 1, 2, and that ends up being this diagram. So this ends up equaling, and again, you can do this sort of more algebraically in terms of the symbols gamma I, but this ends up being gamma 1 squared transfer gamma 1. And more generally, so here's the sort of the general multiplication rule, is that if I have sort of I and J here, and multiply it by some K and L, there's going to be two terms. One where I sort of stack the first columns together, so I plus K and J plus L, blocks on the second. And then it goes the other way around. You sort of match things the other way, I plus L, and then J plus K. These are the heights of these different columns. Let's do one more. So let's look at this gamma 1 transfer 1, 2 times gamma 2. All right, so it's this times that. Well, the coproduct of gamma 2, which is really the first divided power of itself, is, as we said, it's then just going to be gamma 2 1 tensor gamma 2 divided power 0, if you will, and that's just 1 in degree 0. That's a convention with the divided powers algebras, and then plus the reverse. So in other words, it's primitive. And so there is no part of the coproduct that that is on component 2, tensor component 2. This is on this is in cohomology of BS4. I'll go ahead and use the R's. So this is so in other words, what we're saying is delta 2, 2, gamma 2 is 0. And that implies that this product equals 0. And the other way you can kind of think about it, if you want in general for this to be somehow stacking, that there's sort of these diagrams are some sort of apartment buildings, and this apartment building is not allowed or is set to 0 or something like that. So so through these additive basis and these multiplication rules, let me make a claim and leave it as an exercise. the cohomology of BS4 or R4 is generated by, I'll go graphical, this class, so this is again gamma 1 transfer 1 2, this is gamma 1 second divided power, and then this is this new gamma 2, which is a bit bigger. It's got 1.5 times the area of the previous. Modulo, actually there's only one relation you need, namely the one we just talked about. Okay, so this follows, again, all just from the statement of the main theorem and then just the definitions of Hopf-ring distributivity, primarily divided powers, structure, etc. As you go further, it turns out that the number of generators is some function that's hard to understand, and the set of relations grows in some way that's hard to understand. So on the one hand, what is easy, so the claims are that it's straightforward to produce additive bases of Rn. Let me just give one more example. I'll be pretty quick. For R6, you're going to have things like this. You could have up to 3 heights. The heights can include 0. You can have things like this. So some combination of these gamma 2s and gamma 1 2s, and then some other heights, and some of these could be 0 of gamma 1s, and that's it. And then for R8, it's a little bit more interesting. Again, we can have, and by the way, the transfer product is commutative, so we can have some, these are now 4 columns, so the diagrams have width n over 2, or R2n has within diagrams. You can kind of mix and match the types of columns. Some have these 3-2 blocks and 1x1s. Again, things could be empty. I can also have 2 different sets of 3-2 blocks. And finally, in R8, there is a new Hopf-ring generator. It's got degree 7. This is gamma 3. You do have old divided power. But you also have divided powers like gamma 2 divided by power 2. This is in degree 6. And you also have gamma 1 divided power 4. And these end up giving you a polynomial algebra, and you can kind of stack them. And so these are sort of new. These are transfer indecomposable with 4 diagrams. So it is straightforward to produce additive bases of Rn. It's also straightforward to after you get used to it, to multiply. And that's just the cup product. The transfer product is basically juxtapose, not juxtapose, but really place diagrams next to each other. Remembering that if you ever repeat something, there's a divided powers structure around. So with the idea that any repeated columns, exactly twice repeated columns, goes to 0. If something already had repeated columns, it was divided powers, then there's again these binomial coefficients. Let's spell that out. Right, and it's straightforward to multiply, and that's cut multiply, but it's hard to understand. So it's straightforward to just perform the multiplication of two additive basis elements. Let me give one more example. And again, I'll just do this purely graphically. Hopefully that won't be, let's see, let's do, BS8. Let's, let's do this, say. And the point is that you need to stack things, but let's sort of graphically, if I take both of these and try to stack them on top, I'll get 0 because ultimately because the coproduct of this this bottom block is 0, the delta 2 coproduct. So this is a non-trivial transfer product itself. And so that term is going to be 0. So I have to look for ways to stack this here, and I can either stack the 2 with the 1 and the 1 with the 0, or vice versa, right? And so I'm going to get 2 terms. So this is essentially along for the ride. But then the second term would be something with 4 solid, sorry. But this has repeated columns. So again, by the divided powers structure on the transfer product, that's 0. So, so this is just something to get used to, how this Hopf-Ring multiplication works. You're applying this coproduct distributivity all over the place. You get used to it, and you use the graphical notation, and you can become pretty fluent with this. But then the ultimate point is that it's still, for example, generators and relations end up being necessarily complicated. There are papers from the 90s where people sort of list these things out, and it ends up being, even for BS12, something like, I don't know, 15 generators and 21 relations or something like that. Maybe you have to go up to BS16 to be so quote unquote bad, but yeah. So this is the way the calculations work. I next want to then talk about the geometry of these classes. This is just what the cohomology is. I mean, includes a cohomology of RP infinity. We're not saying anything about, the cohomology of RP infinity. The cohomology of projective spaces is represented by other projective spaces inside, and or the cohomology of configurations of points. And I said what the gamma i's are. So gamma 1 is sort of 2 points sharing a coordinate. Gamma 2 is 4 points sharing a coordinate. Gamma 3 is 8 points sharing a coordinate. How these products work with geometry, what the relationship is with Fox-Neuwirth. Again, there's still some things that I don't know there, but in any case, this gets us a a foundation for our for the calculational side, and hopefully we'll be ready to build on that